Welcome to The Explainer. I am so thrilled you're here with us today because we are unpacking a mystery that has literally haunted financial economists for over 4 decades. Back in 1983, a highly cited paper by Mies and Rogoff dropped an absolute bombshell on the world of finance. They discovered what quickly became accepted as an undisputable fact of life: that sophisticated, highly complex exchange rate models simply cannot outperform a naive, random walk when it comes to out-of-sample forecasting. Well, today, we're going to break down exactly what that means, the math behind it, and most importantly, a brilliant piece of modern research that flips this 1983 consensus completely on its head.
Okay, let's dive right into this. Here's our roadmap for today. First, we'll look at the unbeatable random walk. Then, what is a unit root? Next, magnitude versus direction. After that, the adjusted error metric. And finally, the ultimate test, profitability.
All right, Section 1, the unbeatable random walk. Let's look at that 1983 consensus. To really appreciate the twist in our story, we first have to understand the brick wall that forecasters have been banging their heads against since '83. And it comes down to this: can anyone actually predict exchange rates? For years, the academic consensus was just a resounding no. Economists blame this failure on everything from sampling errors to model misspecification, but the accepted baseline was crazy. You could spend literally thousands of hours building this incredibly complex structural model, and it would still lose to a process that effectively just guesses randomly.
Now, you might be wondering, what exactly is this random walk anyway? Well, in time series forecasting, a random walk basically means the expectation of any variable is just its last value. The data is just moving about completely randomly. Shocks to the system are persistent, and the level isn't trending towards any sort of long-term mean. So, if yesterday's exchange rate was $1 and today it moves by a totally random, unpredictable error term, predicting tomorrow's rate with any certainty is statistically impossible.
Moving right along to Section 2, what is a unit root? Let's dig into the underlying math here.
To truly grasp why exchange rates act like these random walks, we have to look under the hood at the econometrics. So in time series models, one of the crucial baseline assumptions you need to make good predictions is covariance stationarity. And a huge part of that is having a mean reverting level, basically a baseline that the data naturally pulls back toward over time. But look at what happens when a specific variable, the lag coefficient, or B1, equals exactly 1. Because the math to find that mean reverting level requires dividing by 1 minus B1, if B1 is 1, you are literally dividing by 0. The mean reverting level becomes completely undefined. The variance just increases infinitely the further you look back. It totally ruins our ability to perform regression because there's absolutely no underlying trend. We call this mathematical dead end a unit root.
And this brilliantly illustrates exactly what it feels like to encounter one in your data. As one analyst framed it, imagine your prediction is a leaf floating smoothly down a river current. A unit root? That would be a whirlpool along the way. Once your leaf hits that whirlpool, your time series gets stuck. It just swirls around that area randomly, and all predictive value is instantly, totally lost.
Now, there is a super fascinating exception to this randomness, and it's called co-integration. Imagine a boy and a girl running around a park completely randomly. Knowing where the girl is tells you absolutely nothing about where the boy is, right? They're independent random walks. But what if the boy is infatuated with the girl? They're still running in random patterns, but every few steps, the boy kind of runs in her general direction. Suddenly, if you know where the girl is, you have a pretty good idea of where the boy is. They are tethered together. In econometrics, we say these two random walks are now co-integrated. But honestly, unless you have that special co-integrated relationship, non-stationary data with a unit root is a massive headache. So how do statisticians actually deal with it? Well, first, they identify if their regressions are spurious, meaning fake. Second, they run what's called the Dickey-Fuller test. Remember how a unit root happens when b1 equals 1? The Dickey-Fuller test essentially asks the data, hey, is b1 minus 1 equal to 0? If the answer is yes, boom, you've got a unit root. Finally, if they can actually difference the data to make it stationary, they apply forecasting methods like the Box-Jenkins procedure.
Okay, Section 3, Magnitude versus Direction. This is where our story takes a massive twist.
Remember that 1983 paper claiming models absolutely can't beat the random walk? Well, modern researchers Imad Musa and Kelly Burns realized that the 1983 conclusion might be perfectly true, but only because they were measuring success the wrong way. So the crucial point is this: how do you actually define a good forecast? The original researchers used a metric called root mean square error, or RMSE. RMSE strictly measures the magnitude of the error, like how far off, in absolute numbers, was the prediction from reality. But Musa and Burns argue that in finance, getting the exact number right is often way less important than just getting the direction right. To measure that, they look at the confusion rate, or CR. The confusion rate simply calculates the percentage of times a model predicts the wrong direction of change, like, predicting the currency goes up when it actually goes down.
To prove just how radically different these metrics are, the researchers generated 100 random observations simulating an exchange rate across 8 hypothetical models. If we judge by RMSE, that classic metric, Model H is our absolute winner, ranked number 1. But notice Model H's confusion rate. It ranks 6th out of 8 for predicting direction. That's not great. Now look at Model A. It's perfectly flipped. Model A is terrible at predicting the magnitude of the error, ranking 5th in RMSE, but it is the undisputed champion of predicting direction, with a stellar confusion rate of just 0.09. The rules of the game completely change the winner here.
Which brings us to Section 4, the adjusted error metric. Let's look at a mathematical compromise. So we've got a clear conflict, right? Some models are great at magnitude, others at direction. How do we evaluate them fairly? Musa and Burns proposed a brilliant mathematical compromise, the adjusted root mean square error, or ARMSE. They literally just took the conventional RMSE formula and multiplied it by the confusion rate. It's that simple. This creates a beautifully balanced measuring stick. If two models have the exact same magnitude error, the one that predicts direction better gets the higher ARMSE score. And by setting their weighting variable m to 1, they created a metric that mathematically eliminates any bias toward either magnitude or direction. Now, what's really interesting about this slide is how the RMSE ranking shifts our entire perspective. Looking at the gray bars, that's our new combined RMSE metric. Model H, which was the king of magnitude, still holds on to the number 1 spot overall because its magnitude errors were just that small. But consider Model D. It was awful at both magnitude and direction, and the RMSE rightfully punishes it, dropping it to the absolute bottom of the pack. When the researchers tested these models against the random walk using this new balanced metric, the models suddenly looked far, far more competitive. All right, final stretch. Section 5, the ultimate test, profitability.
But let's be real for a second. We are talking about finance here, and an academic error metric doesn't pay the bills. Economists have long been puzzled by this massive contradiction. If random walk models provide free forecasts that are statistically just as good as professional models, why do profit-maximizing firms pay millions of dollars for professional forecasts? Well, the answer is that error metrics bear a very weak relation to actual profits. The ultimate practical test of a model's power is whether you can actually use it to execute a profitable carry trade, shorting a low-interest currency and taking a long position on a high-interest one based purely on your model's forecast.
So, when the researchers ran their simulated carry trade, they measured the results using the Sharpe ratio, which calculates risk-adjusted returns. Remember Model A?
The one that was terrible at predicting the exact magnitude of the exchange rate, but absolutely amazing at predicting the direction? Model A pulled in a Sharpe ratio of 0.96. That is an incredibly strong risk-adjusted return.
And this perfectly illustrates the entire point of this explainer. Model A ranks number 1 in profitability. Meanwhile, the random walk, the so-called unbeatable champion of the last 40 years, ranks a pretty mediocre 5th. The researchers definitively proved that the rank correlation between profitability and direction accuracy is massively higher than profitability and magnitude. Simply put, in the real world of trading, knowing which way the currency will move is far, far more valuable than knowing exactly how much it will move. By using profitability and direction as our criteria, exchange rate models absolutely can outperform the random walk.
So that 1983 consensus wasn't necessarily wrong about the math. They just brought the wrong measuring stick to the game. They optimize for textbook error while the market optimizes for direction and profit, which leaves us with a fascinating, provocative question to end on. If exchange rates aren't an unpredictable random walk, what other accepted, undisputed facts in finance are currently hiding behind the exact same illusion? I'll let you ponder that. Thanks so much for joining me on this explainer, and keep questioning the data.